So, welcome to Chapter 14. This is actually Part A. So Chapter 14 overall is on ideals, quotient rings, maximal ideals, prime ideals. It's a pretty hefty chapter, in fact, so I'm going to actually divide it into 3 sections. So Part A is just generically on ideals. But the intro for this will sort of be an intro which will lead us into the entire chapter, at least the first 2 sections specifically. So the intro is that in group theory we created quotient groups. And the way we did this is we took a normal subgroup n of g, and we created quotient groups or factor groups, depending on which term you want to use, with cosets. And under addition, these cosets look like the following. This was this was G mod n. This was the set of G plus n for G and G. I want to mention the addition notation specifically because that's what will come up here, right? And so this is what we did. And so we could do a similar thing in ring theory. So we can do something similar with rings. So what we need to know is we need to know, like, what do we do instead of a normal subgroup? Like, what's the analogy? Like, we might think like maybe a normal subring or something like that, but it's actually a little bit different than that. So the replacement for a normal subgroup becomes something known as an ideal. It has a slightly different definition. So what we want to do in this part A is I want to define an ideal, give you an ideal test, do some examples, and then look at some very specific examples of ideals which come up frequently. So definition. So a subring A of R. So R is the big ring, A is the subring. This is called an ideal of R. So if the following is true, for all A in A and for all R in R, we have AR and RA in R. So in other words, if you take something in the subring, the ideal, and you multiply it by anything in the ring, you get something that's in the ideal itself. And it doesn't matter which way you multiply it. So we're not saying R is commutative, but it makes no difference which way you multiply, the result is still in R. Now there is a concept in more advanced ring theory about a left ideal and a right ideal, where if you multiply it on one side, it is, and the other side it doesn't matter. Everything in this course is basically a two-sided ideal, or just an ideal. So before I give you some examples, I'll just say one other definition, that an ideal is proper if it's not the whole ring. So if it is not all of R. So here's some examples just of ideals in general. So in any ring, both the subring consisting of 0 and the whole thing are ideals of R. So those are pretty easy to see. So second one, a little bit more work to see, but just if you give it a think, it's really easy. So NZ for n an integer is an ideal of Z. This is because if you take something in NZ and you multiply it by any integer, you get something in NZ, right? So for example, i.e. specific example, say something like 8Z is an ideal of Z. Because if you take a number in 8Z and you multiply it by a number in Z, the result is in That looks like a dollar sign. That's a number sign. Yeah, the result is in 8Z. Right? And it doesn't matter which way you do it. Right? The multiplication is commutative here, so it makes no difference. And something a little less obvious, but still pretty easy to see, is if you let the ring, so let's say in the ring Zx, so Zx is all the polynomials with integer coefficients. Let's look at let's say the set of all polynomials with integer coefficients and constant term 0. Right, this is an ideal. And so just to see that with an example, here's like this isn't a proof, but if you take something in Z, right, so say like any polynomial whatsoever, and you multiply by something with constant term 0, I'll put the 0 there just as a placeholder. When you multiply these two, the constant term will be 0. This is a polynomial with constant term 0. And this will happen no matter which two polynomials you use, as long as you take one thing in the ideal, something with constant term 0, and multiply it by any polynomial in the world, you will get something with constant term 0. So these are three very, very simple examples of ideals, but they're three good examples nonetheless. So next we want to have is a test for ideals. So B, theorem, ideal test. We won't actually use this much. The reason is that the reason for having it is because of the couple places where it is useful. But the reason we won't use it much is most of the time the things that we say are ideals will clearly be ideals. Like there'll be no big surprise. It'll be fairly easy to see that if you take something in the set and multiply it by anything in the ring, you get something in the set. So this will be a minor issue for us, but it's worth mentioning anyway. So the ideal test says the following. It says if A is a subset of R, this is a ring, and A is non-empty, then A is an ideal of R if the following two things hold. So I, for all A and B in A, we have A plus negative B in A. We can write this as A minus B as well. I just wrote it this way so we can think of it as A plus the additive inverse of B, but think of it as A minus B if you like. And 2, if for all A in A and for all R in R, we have AR and RA in A. So the proof of this, for what it's worth, is basically a mashup of the subring test and the definition of an ideal. In other words, a combination of those two. I won't go through a formal proof of it. The point being is the note here, we won't use it much, if at all. I'm going to mention it briefly in a minute. Again, and then possibly never again. So last thing then in this section is to look at two, really kind of one, but two classic ways that ideals can arise. So classic types of ideals. So definition. So both of these definitions and a bunch of things actually in this section rely upon having not just any ring, but a commutative ring with unity. In fact, most of the rest of the semester, most of the rings we ever look at will be commutative and they will have unity. So in this case, if R is a commutative ring with unity, Don't forget, a unity is a multiplicative identity, so think of it as just like the number 1. When you multiply by anything, it leaves it alone. So if R is a commutative ring with unity and A is in R, then what we have what's called the principal ideal generated by A. This is a really long definition. What this is, so the notation is familiar, but it's not what you think. Right? It looks like the group generated by notation, but it's not. It doesn't mean the same thing. So this is the set of RA for all R in R. So in other words, you take the A that you're given, you multiply by everything possible in R. It doesn't matter how you multiply it because it's commutative. So you multiply by all the things in R and you get a result. You take that set that's the result and you get an ideal. Now it's not screamingly obvious that it's an ideal. This does need to be checked using the ideal test, but nonetheless, this is like a classic way of getting an ideal. So 2 notes. Note 1. This is the same notation as group theory, but different meaning. So it's the same notation as this which we had in groups, but different meaning. Remember, in groups it meant all the powers of G. In this it does not mean that at all. And the note 2 is the proof that it's an ideal you can do formally with the ideal test. So the proof that this guy, so give it a go, it's not hard, that this is an ideal is done with the ideal test. So let's look at an example before we expand this definition. So an example, let's say, look at in the ring Rx. So this is all the polynomials with real coefficients. Let's look at the ideal generated by x squared. So x squared is a polynomial. It's something in that ring. So this is what we have. Right? The ideal generated, the principal ideal generated by x squared. So this is the set. So I take anything in the ring, so any polynomial, and I multiply by x squared. So if you think about what happens when you do this, the polynomial p sub p of x, that guy right here, when you multiply it by an x squared, you'll basically lose the constant term and the x term. Like they don't go to 0, but they go to 0 in the sense they all get bumped up by 2 degrees, which means the result is all polynomials with constant term 0 and x term 0. So things like 5x cubed plus 2x plus 0x plus 0. Right? You don't need to write these two, but they're there. I just put them in there just so we can see, because they're gone when you multiply them by x squared. They get bumped up a degree, or 2 degrees rather. So this idea, this principal ideal generated by A, will come up a lot, and it comes up so frequently there's sort of an expansion to it, and that's the following. So expansion is a bad word. Generalization is a better word. So the generalization is as follows. So given a bunch of A's in R, that's a ring. It's again, just to be clear, it's a commutative ring with unity. So we define this guy. So this is called the ideal generated by A1 through AK, not the principal ideal. The term principal is only used when you generate it by one thing. So this thing, I'll write that term in a second. This is the set of all. Basically, I get to make any linear combination using coefficients in R. So all these R sub i's are in R. This is the ideal generated by the AIs. So let me just end with an example of one of these. So in ZX. So ZX is the polynomials with integer coefficients. Take a look at the ideal generated by X and 2. These are separate entities, X and 2. And so what this means is, right, so this is, so if you look at this, it means I get to take all linear combinations of X and 2 where the coefficients, quote unquote, are polynomials. So if you think about what happens when you do this, right, this second part, so let's do it actually in pieces. The first part will have no constant term, because the X bumps everything up a degree. The second part can have a constant term, but the constant term must be even because of the 2. In fact, all of the coefficients will be even, but specifically, actually, let me say that, even though it'll be the constant term is a relevant bit, but here all the coefficients are even because originally they're integers. So if you combine these two, think about what happens. In the first part, you can have no constant term, but the coefficients otherwise can be even or odd. It doesn't matter in that first part. In the second part, the coefficients are all even. When you add these, the constant term will end up just coming from the first part, right? Like the constant term comes from here. The rest of it can give you anything for a polynomial. So the result of this is all polynomials. So all polynomials in ZX with even constant term. Right, every other term doesn't have to be even or odd because of the P of X times X, but the constant term must be even in this case. So again, this is an example of an ideal. So just a final closing note is if you're curious why we need to have a commutative ring with unity in this case, I'll just say it really, really briefly, is the commutativity is there just to simplify the way that you do it. Otherwise, the notation would need to be tricky, right? Because if you wanted to have the ideal generated by x squared, for example, does that mean you multiply it on the left or on the right? And are they different? And the test suddenly becomes different. So it's basically to avoid computation. It's to avoid complications. So commutativity avoids. You could do a lot of this without commutativity, but the situation just gets uglier. So this just avoids complications. And having a unity, having a 1 ensures that, say, the ideal generated by A actually contains A, because A is 1 times A. So A itself is 1, which is something in the ring, times A, and will be in here. Otherwise, you might have a situation where the ideal generated by A doesn't have A in it, and that just seems a little odd. So we demand that a unity be in it, so we sort of get sensible behavior. So that's the end of part A. That just introduces the concept of an ideal, and the ideal is generated by a single thing, and the ideal is generated by multiple things. And in part 2, what we'll do is we'll look at quotient rings and see what can happen there.